All right. I'm Richard Csaky. I'm doing a PhD in the intersection of neuroscience and machine learning at the University of Oxford. I recently started the Oxford Science Podcast to learn more about the diversity of science done in Oxford and the people behind it. The aim is to have long-form, open-ended conversations and delve deep into the science. Today, I'm very honored to have Chris Lintott as the third guest on the podcast. Chris is an astrophysicist at Oxford and is known for his work in the field of galaxy formation and his involvement in various citizen science projects, most notably Zooniverse. He's also an engaging science communicator and has co-presented the long-running Astronomy TV show The Sky at Night in the UK. He authored several books, and I had the pleasure of reading The Crowd and the Cosmos, where he describes how citizen science has contributed to expanding our knowledge about the universe. I'd like to thank you very much for agreeing to have this conversation, and feel free to expand on anything I omitted from your introduction.
Yeah, it's a pleasure to be here, and I've got coffee as well, so we're well set.
Yeah, all right. So I would like to start with the book, with Crowd in the Cosmos. I really enjoyed it. So I was wondering if you can describe in brief what this book is about and what motivated you to write it.
Well, there's sort of different questions. So the book is broadly about this topic of citizen science, which is the engagement of everyone in the scientific process. And I feel like it's something that I've been thinking about for as long as I can remember thinking about science. I grew up as a small kid with a telescope, but rather than just look at the same things night after night, I was obsessed with the idea that I might discover something, that I might find a comet or a storm on Jupiter or something like that. And amateur astronomers, people with telescopes in their back garden, do that sort of thing. Certainly in history, there are all sorts of things that have been discovered by what we now call citizen scientists, and still people find supernovae and exploding stars and all sorts of things. Whether you could do that now with the kind of telescope I could afford to buy after selling ice creams on the seafront in my hometown, I'm less sure. But as I grew up, as I made my way as a scientist, I realised that the problem's actually the reverse. We don't necessarily need amateur astronomers to provide data to us these days. In some areas they do. What we have is too much data and not enough people to look at it. And so we early on, so sort of 2007, we had this problem of having too many galaxies. So we had 1 million images of galaxies. Machine learning then wasn't up to the job of sorting them out by shape, which is what we wanted to do, because the shape of a galaxy tells you about its history. And so we asked for help online with a project called Galaxy Zoo. And I really thought, I was thinking of it as something that the old school amateur astronomers would do. I'd go and give a talk to an astronomical society, maybe 50 people, and those 50 people go home and maybe they classify 50 galaxies. And if we did this a few times a month for 5 years, we'd get through our galaxies. It's a nice engagement project. But the web doesn't really work like that. It's hard to succeed slowly. And so within a day, we were getting 70,000 classifications an hour. And the book, The Crowd and the Cosmos, is the story of what happened next as we expanded that to the Zooniverse, which is this platform that now has a couple of million volunteers and 200 projects, but also tries to think about the role in the future as machine learning gets better, as new data sources come on stream. The book is an attempt to argue that there will still be a place for human perception and for citizen scientists, even in what are some quite high-tech projects.
Yeah, I think you mentioned that machine learning can augment humans in classification rather than replace them completely, which was...
Yeah, that's right. And that's a lot of my work now, is working with excellent students and postdocs on trying to think about how to do exactly what you say, to combine human and machine intelligence. So I think the narrative, certainly if you read the press, and you do some deep learning, I know, but the narrative is that machines will slowly replace us in different fields. And the evidence for that's pretty weak. I think what is happening is that people who get better at learning to work with machines have an advantage. And that's true in science as well. So we find in many of our projects that the combination of citizen scientists online, of humans plus machines, outperforms either on their own. It seems to be a general. There's some nice examples. There's a whole group of people who play hybrid chess, where so sort of chess as an open book exam, where you can have you can use a chess computer, but you make the moves. And the interesting thing about that example is that the people who win in such circumstances are not necessarily the best chess players. They are pretty good chess players, but the skill that matters is being able to collaborate with the machine. We're finding that in our science, particularly in the fun bit, which is finding unusual stuff, of finding really rare examples
outliers.
Of things. Outliers, but interesting outliers. Yeah. So this is the thing. Finding outliers, like if you have a large data set, there are lots of good machine learning ways, which we could talk about, of quantifying how unusual a particular image is, say. But finding which of those unusual ones is interesting is a very human skill. And so I sort of have this general sense that the machines are going to tell us where to put our attention, and then we'll need our citizen scientists or our professional scientists to decide what to act on, to decide where the unusual things are. It's another strand that runs through a lot of what I've done in my career, and my interest in astronomy is this sort of sense of paying attention to the unusual. I think it partly comes back to being that kid with a telescope trying to discover something, but it's also true that there's a kind of science that sometimes gets neglected, where you stumble across something, in my case an unusual galaxy or a star that's behaving in a way that you don't expect, and those examples can teach you a lot about the physics of the universe, just as a systematic survey can.
Why do you think it's neglected? Because to me it makes sense to focus on the...
I think it's neglected for a couple of reasons. I think we teach science, or we talk about science often as a hypothesis-driven endeavour. Like a lot of the time we like to talk about the results that we get as if we had an idea, we designed an experiment, we tested it. In my world, at least, astronomy is a very observational science. Sometimes it feels more like doing sort of archaeology, digging up bits of the past out of data. It's reasonably rare to act like that. Sometimes it's possible, often when you're asking big questions like measuring the speed of the expansion of the universe. But a lot of the time we're sort of working backwards, that the exciting moments are not somebody running down the corridor shouting Eureka. The exciting moment is somebody with an image they don't understand, or an object they don't understand, or a behaviour they don't understand. And I think those are more complicated scientific stories to tell. If you come and try and do that as a press story when you've published your paper or whatever, then I think it's slightly harder to explain the fun of that and explain why that's important than it is to say, we tested Einstein. I have this particular pet hate in physics that almost any result that deals with fundamental physics of the universe gets framed in the papers as, have we tested Einstein proved right again? And the reason we do these experiments is sometimes to test relativity, but they're often for other reasons, because they tell us other things. But it's much easier to frame it as a test of relativity, because then everyone can understand. We pass the test or we don't. We understand something or we don't. Whereas actually, we're often opening up what I think of as... So there's an argument in my field about observatories versus experiments. So an observatory is a multi-purpose thing that can live for a long time and do many different types of science. The Hubble Space Telescope is a good example. Most of the things that you'd list now as the Hubble Space Telescope's greatest hits weren't in the original plan.
So are these like things like general sky surveys?
Yeah, for example. So a sky survey where you share the data is a good idea. A nice example, which actually provided the data for Galaxies, is something called the Sloan Digital Sky Survey, which is, I joke, is what happens when particle physicists build a telescope. So this was built, it's on a mountain in New Mexico. Though it's been used for other things since, it was built to do one job, which was to scan the whole sky. For 8 years, it just let the sky pass over its camera, and it took images of billions of objects. And then there are about 1 million nearby galaxies in there, and on clear nights, at the clearest nights, it went and measured the distance to those galaxies. So you've got this three-dimensional map of the sky, of our local universe. And the main reason for doing that, the reason that the Department of Energy in the US put money into that, was you can use features in the structure of those the distribution of those galaxies as a ruler, and you can measure the expansion rate of the universe, which is a big fundamental question. But to do that, you don't need to take pictures of the galaxies. You just need to know where they are. They're point particles, essentially, tracing the distribution of matter in the universe. And yet, people who built Sloan, for reasons that no one can quite pin down, decided to spend long enough on each object to take a decent picture of it. And so this produced this catalogue of images of 1 million galaxies. And more science, not always about the quantity of science, but all sorts of unexpected science, and thousands of papers have come from that repository of images, rather than just the measurement of the expansion. So one decision converted that from what I would call an experiment, where you're testing a hypothesis and you're going to make a particular measurement and you're going to understand its significance, to an all-purpose observatory where the data, Sloan has found asteroids, it's been used to find supernovae, it's informed great renaissance of what we know about how galaxies form and evolve. It's produced some pretty pictures, an awful lot of galaxies that look like blobs as well, but we'll work on those. And then the team made the data open. So that's an important part as well, so that everyone, and did a good job documenting it. So it becomes an observatory for everyone, and then you can have these sort of scientific accents. I've just written, actually copy editing the final version, a book about this style of science that comes out next year, which in the UK is called Our Accidental Universe, but we're playing with ideas for an American title. They want something a bit more fun, and we're thinking maybe Happy Little Accidents or something like that sense of being surprised by what's in your data.
So one motivation for the book was to share this kind of passion and excitement that came from your early days of discovering.
For Crowd in the Cosmos, yes. I think I do a lot of speaking about astronomy, I always have, and I found that talking about Zooniverse projects felt fundamentally different. There's a big difference between being on stage telling an audience about things that I've done and that my clever colleagues have done. That's fine as entertainment, but it can be alienating for people. There's a sense that science is something done by people in universities, by people who are good at maths at school and that sort of thing. Whereas talking about the Zooniverse, we're genuinely talking about results that hundreds of thousands of people have contributed to in their spare time. And I found that shifts it. So part of the point of the book was to convince people that they can have an active part in science, that it doesn't have to be this thing that you're a fan of, maybe, but that's done in remote laboratories and ivory towers.
So you could say it's a recruitment book then.
Yeah, it's partly that, for sure. I'm not sure I care whether readers... This is going to get me to try. I'm not sure I care whether people who read the book go and do Zooniverse, but whether they do Zooniverse or not, I think I care that when they read an article that says that coffee either cures or causes cancer, that they feel empowered to ask the next question, which might be how big's the data set, or it might be to read the abstract of the paper, or to get over the barrier. I think as a science communicator, I'd be very inspired by an idea from the museum world where people talk about a thing called threshold fear. So whether you go to museums, even if they're free, particularly art museums, depends a lot on whether your background, whether your family took you there as a kid, whether you knew people when you were growing up who went to museums, who had art as part of their lives, who had things hanging on the wall, and whether you're likely, if you're in a city, whether you're likely to go to a museum depends on whether you've already decided that you're the kind of person that gets something out of looking at a painting. And nothing the museum could do. They can have the most engaging exhibition, the best labels, they can display work that's relevant to all sorts of different communities, but none of that's going to persuade people over the steps and into the threshold. And in science, I think we have that a lot, right? People find it difficult to engage with science because they've never met anyone who is engaged with science. They didn't grow up in a household where they knew people who were scientists or had scientific hobbies, then as an adult, I think that world feels closed. And Zooniverse and talking about Zooniverse and writing about Zooniverse, I think, and we have some evidence for this in some of the studies of the participants that we've done, is a way of getting over that threshold. People who it's one thing to say, I have questions about the universe, but if you found an unusual galaxy, you want to know about it, and you're motivated to learn quite a lot, and then you can find resources that work. So I do see this sort of stuff as a activating energy that gets people over these thresholds and into whatever their journey in science is.
Yeah, it's quite interesting you mentioned the coffee example, because I feel like that's something that's recently been a lot in discussions, especially online, is how much you want to question science.
Right.
And how much you want to defer to experts. Like, we've seen this with COVID, for example. But I feel like the last few years, definitely the general public have been trying to question more, maybe, and figure out for themselves. But it's interesting what's the right balance, right? Because you don't want to question everything.
Yes, well, I think you have to be really careful, I think, because you can end up in a position, and some of the commentary on COVID has done this, where you're saying actually just blindly trust the science, and that's difficult. But I was very conscious during the pandemic that I had a set of tools that I could use to make decisions. So, things like I can read a graph. Like the language of physics is the language of graphs, right? And so I understand what a log scale is, and so I could understand data about the prevalence of COVID. That is not a skill that most people have encountered. Yet on our Planet Hunters project, which has people looking for planets around other stars, people look at graphs for fun. And so there's a skill that's developed there. There's a filtering, right? I knew how to ask the right questions, and I could assess on Twitter, particularly, people who I thought were talking sensibly about the evidence from those who weren't. And that's a scientific skill as well. So I think it's a skills development piece. We don't want to say to people, just trust the science. We want to say to people, here's the skill set you need to determine whether a scientific claim is meaningful or not. Is that study relevant? How many people was it conducted on? What's the significance of the evidence? Who is it that's promoting it and why? These are all sort of science skills, but they're not what's taught as science in schools, right? Or at least not in this country, right? That's not how we talk about basic biology in schools. We tell people some nice stories about evolution and get them to learn that there are 4 bases on DNA, all of which is important, but none of which helps you when you're trying to decide whether to wear a mask or whether to pull your kids out of school or whether to go and see your elderly relatives. So I think, COVID has been a really crystallizing moment for science communication for me. It really illustrates which things we've done well. And I think 20 years ago, I think the information would have been hard to find. And I think because of moves to open science and some of the ways that gets translated, I think that's been better. But it's clear that we haven't got to the point where people are comfortable doing more than ending up on one side. Lots of people end up on one side, believe the science or don't believe the science, and not much in between.
Yeah, so, but I guess there's a question of, is there too much information now out there? And how do you filter that?
Isn't that the problem of I don't know what it's like in your world, but when you come into the lab in the morning and you look at the papers that came out yesterday, don't you feel there's too much information?
It's overwhelming.
Yeah.
Deep learning is notoriously a very fast-paced field.
That's true, and computer science publication is slightly crazy. So there's information all over the place. No, that's true. So I don't think that's a problem to do with the public consumption of science. I think that's a problem to do with our networked world. And so, but you have tools, and maybe, and some of those tools are literal tools. I'm sure there are filters and search engines, but we also rely on our networks, right? So I read papers because I find out about them from friends, or because somebody comes into the office and says, "Have you seen this?" This
or Twitter.
Or astronomy Twitter has been. This is we can get into the politics of Twitter at some point, but astronomy Twitter's. I think I'm up to 3 separate papers that have come out of Twitter conversations with people. It is a really rich place. And so I think what we need is those, you see this in citizen science as well. We see learning from participants in Galaxies or Planet Hunters or any of these projects. We see people teaching each other how to use tools and how to filter information. So there's some, if people have the motivation, they can also use those soft skills and those networks to find the information that they want, but expecting them to do so without any previous contact with science is really hard. So anyway, this, the Crowded Cosmos isn't a book about how to solve science communication, but I do think these questions come up, as you say, once you start saying, I want people to participate in astrophysics or in research on climate change or on whatever else it is.
Yeah. I'd like to go back a bit in time, because you mentioned in the book your fascination with the school telescope.
Yeah.
And I was wondering, where do you think your passion for astronomy comes from more fundamentally, if you can?
Yeah, it's a really good question. Because I remember looking through a telescope for the first time, and it was when I was about 8, and we went to my parents took me to a public observing night at the observatory at the secondary school I ended up going to, and I looked through the telescope at a star called Albirio. And Albirio is you can see it in the sky tonight. It's in the constellation of Cygnus, which is the Northern Cross. It's really obvious at this time of year, and Albirio is the bottom of the cross. And it just looks like a normal star, but through a telescope, it's a double star. And one of the stars, to my eyes, is blue. One of them is yellow. Color perception is weird in astronomy, so people see these stars as different colors, but most people say they're sort of blue and yellow. And I now realize when I looked through the telescope that it was out of focus, but I saw these two stars as large orbs, and I thought I was seeing the star. And that fundamental idea that something that looked straightforward to the naked eye, but I could get more information, it could look spectacular. I found magic then, and I find magic now. We could take it to extremes. The Hubble Space Telescope spent a couple of weeks over Christmas in 1995 staring at the emptiest patch of sky they could find in the northern sky. And then when you look at the image, which is the Hubble Deep Field, it has thousands of galaxies in it. There's something magical about that. And the associated idea that hooked me really early was that we're here on a planet around an ordinary star. It turns out this is a fairly ordinary planet, as far as we can tell. And we can make statements about how stars form, about how our universe began, about how it will end, about whether there's life out there. And that connection of observation to big questions was the thing that got me into astronomy. There are other reasons I've stayed, but I think that's the fundamental attraction of the subject, I think.
I imagine it can be similar with people with biology, because you look at your hand with the naked eye, and then you put it under a microscope. And then you see all these cells.
Or we're in Oxford, so Hooke seeing things in a drop of water back in the 17th century as well. I think that's right. There's also a similarity, I think, in that a lot of the field biologists I know grew up as ecologists, right? Bird watchers or people out looking at rock pools or whatever. And I think there is also the sense of, I get to play with some pretty big telescopes now. And though it's becoming rarer, I'm lucky enough, I'm old enough that I spent some of my career going to some of the world's great observatories. And that feels like an upgrade from the small telescope outside my parents' house in Devon to be on top of Mauna Kea in Hawaii or La Palma in the Canary Islands under a beautiful dark sky. So that's sort of photon hunting hasn't gone away either. I think that's part of it. And astronomy got me through school science. I found the school curriculum pretty dull, and was lucky enough to be at this school that happened to have an observatory, and the thing that makes no sense to me, and I don't think happens today, was that the teacher and science technician who'd put it together, Graham Veal and Ian Walsh, who'd led this project to raise money for this telescope, Only a couple of years later, when I turned up as an 11-year-old with a group of friends who were interested, they just gave us the keys and said, use it whenever you want. And I think that thing of being empowered to go and do that and to hang out at the observatory, we spent ages trying to do science with it and always failed. But like that, being trusted to do that was a really important thing.
Did you ever break it or something?
Yeah, we certainly crashed the computer a few times.
That's fine.
Yeah, so that's fine. No, we were quite respectful of the telescope, I think. There's a famous incident where somebody set fire to the carpet using the telescope by accident, by swinging it around in the daytime when the sun was out.
Sunlight was
exactly. But that definitely wasn't me. But no, there were minor things. We dropped an eyepiece, I remember, which was awful. And but no, we took it very seriously because we'd been trusted to use it. And it was a spectacular thing. They've replaced it now with a more modern telescope, which is much less fun. But the observatory is still there.
Yeah, I can definitely relate to like playing with this cutting edge technology that's not very accessible. Because, for example, we have an MRI machine here,
right?
An MEG machine. I think maybe it's a bit less cool than going somewhere exotic.
Yes, you just need to put them on mountaintops somewhere else. And I should say, in almost all cases now, modern astronomers get their data by email.
Yeah.
So,
which is as positive as well as
it's more efficient for sure. I think if we want to stumble, several important things from Galaxies that we found. We found an unusual object called the VOVEP, which is a gas cloud the size of a galaxy. But we got our initial data by asking a friend to accidentally point a telescope at it when he was doing a calibration run. And that's much harder to do now. So I think there's lots of stuff around the edge that suffers. Plus, it's fun to go to these places, but it does make it more efficient. There's no consolation for my students who don't get to go to Hawaii, but get to sit in the office and wait for data to turn up. But you're right; it's a privilege to be able to use these things. You're often thinking. I mean, did you come into your field because you wanted to work in machine learning, or did you come in because you were interested in the brain? Or
I was interested in brain.
Okay.
I came from machine learning.
Okay.
Yeah.
I wonder if there's a generation. There are certainly kids now who are getting to play with all sorts of techniques and tools, whether it's GPT or whatever online, or have access to programming languages like Python. So I wonder if there's a generation of computer scientists who have advanced tools that they can play with when they're 12, 11, 14, 15 and will come through and be inspired by that.
Yeah, I mean, computer science is definitely a very accessible thing because ChatGPT is online, right?
Right, yeah.
You don't have to be at the university to use
it. Yeah, or Kaggle competitions can be entered by anyone or whatever.
Datasets are open.
Yeah, that's right.
Something I really enjoyed in your book is your humanizing of science. I was wondering if you can speak more to how human biases and imperfections affect the otherwise ideal world of science. We're back to sort of the image of science that we talk about often in the media. So I think there's some literal biases. So we've dealt with in our world visual perception problems. So we found that you were more likely to find spiral galaxies when they were anti-clockwise rather than clockwise, for example, which, given that one of the results we were trying to look at was to compare the distribution of the two, then that's a problem. And so we end up having to measure that. So that's just because how the visual system is
I think so. It's either to do with the visual system. People have talked, there's a famous illusion that has a rotating ballerina, but you can do it with any image, where the brain will flip from seeing it rotating left to right. And so it's something to do with seeing a 2D image in a 3D world, probably. It may also be to do with most of our participants came from cultures that read left to right. Mm-hmm. So it may be how your eye interprets the shape, to do with how you read. It was certainly not something as an astronomer I thought I'd end up caring about. But we ended up measuring that. We really must, I keep saying, we must go back and actually do the controlled psychological experiment and see if we can pin down what's going on. We did end up with people with eye tracking devices looking at how people looked at galaxies, and that was interesting because it showed a different kind of bias. So if you show somebody an image and say, what kind of galaxy is this? If they've never done that task before, then the pattern of eye tracking is what you'd expect. It goes all over the image. Whereas once they've seen 20 or 30 of these images, and the main task is this a galaxy with nice spiral arms or not, then what you end up with is people very quickly looking only at the most spiral-like feature. And at this point, you can think of it, I think I call it in the book, expert blindness. So you can start stuff in the background gets missed, and so there's a famous example of this, which is it was a road safety advert. Well, it was an experiment, and then it was a road safety advert where you're told to count the number of passes that a basketball team complete. Exactly. And there's a gorilla, a man in a gorilla suit, or person in a gorilla suit. So people did a version of this where they took X-ray images and showed them to surgeons who were looking for signs of cancer, and they put a cartoon gorilla in the images, and none of the surgeons noticed the gorilla because your brain, when you're in this pattern-seeking mode, you don't see these other things. And so I talk in the book about, therefore, the need for non-experts to be in the field. And I think you can take that more broadly as well. I think there are places in science where experts get stuck in a rut, and you need somebody from outside or from a different discipline to come in and ask a different set of questions. Which is not to say that everyone with their own theory is Galileo and can overturn all of science, but we do have these biases towards existing ideas.
Yeah, I think humans are very good at optimizing if they have something to optimize for.
Yes, I think that's right. And we often do that without knowing that that's what we're doing.
Yeah, exactly. It's unconscious.
Yeah.
And then I guess it's good to have some kind of perturbation.
That's right.
In the system.
Yeah. And in some sense, we can do that by not offering the same task, right? So there's if you ask even a PhD student to classify 50,000 galaxies, which we did, they're going to make mistakes. Because that's an extremely tedious thing to sit and do, and it's repetitive. So you can change the task, but you can also invite other people in as well. And we ended up quantifying, in some of the projects, we've ended up quantifying people's different contributions. And you can see that people who do well on the regular bit of the task aren't necessarily the same people who react well when there's an outlier or something interesting. And so those seem to be different skill sets. The other piece of humanization, I guess, is that I think, and I tried to write a bit about this in the book, I think we forget that there are many modes of being a scientist. So one of the criticisms of our sort of citizen science is that the participants, who are mostly online and mostly participate for half an hour or so, aren't doing real science, that they're doing the drudge work, the classification, and the real work of science is done by those of us who ask questions and then write the papers. But I think that makes a couple of mistakes. One is that there's this quote that gets bandied around from Rutherford, which says, all of science is physics or stamp collecting. But there's nothing wrong with stamp collecting, right? You need to collect your data and find your unusual things. But also, even without the citizen science element, for me to write a paper using the Sloan Galaxies, I have relied on people who've designed and built the telescope. I've relied on project managers who've made that happen. I've relied on database engineers and research software people who've built the software that's done the classification. Trust me, there are people in there who understand camera filters intimately and have added their expertise. Plus there's the people who've written papers before that did the photometry, how bright is the galaxy. We all use the same catalogue that tells us what the basic properties of the galaxy and so on.
You build on a huge amount.
So science is, and there are days where I'm doing the bits that aren't asking a question and writing a paper. And so I think if we can tell more of the stories about how science is done, then we bring in more of those pieces, and then we get further from the myth of somebody in a white coat running out of a lab waving an idea and winning a Nobel Prize for it.
Yeah, I think definitely that perception is shifting.
Yeah, do you think?
Yeah.
That's good to hear. Yeah. I think COVID helped, weirdly, because though the media, there are a few people like Sarah Gilbert who led the Oxford effort for the vaccine. I think people talked about their teams, and it was obvious that there were large teams of people working on these things, and that there wasn't a single hero of the pandemic.
Yeah.
There was this vast industry of science that made a difference.
Yeah, I mean, being honest, being upfront about it. So, for example, something that always springs to mind related to this is the gravitational waves paper, which has like 2,000 authors or something.
Yeah.
So, yeah, that's a very extreme example. But...
No, exactly. Well, particle physics has been in this for a while. Though there's a sociology of science as well. Like, one of the things that I like about astronomy, or my kind of astronomy, is that I work in groups of about 10 people. So I would, I have huge admiration for the LIGO, the gravitational wave people, but I don't want to particularly spend my life in a team of 1,000 people. I mean, I have enough telecons as it is. But so in science, there are experiments on all scales. And another bias is, I think, that we tend to talk about the big efforts and forget that we can sometimes get knowledge from the fact that 4 or 5 people have a good idea and follow it up.
Yeah, but I guess your group of 10 people, like you said, also builds on...
Oh, yeah, of course. And we're using open data and so on. Yeah. No, that's true.
Let's go a bit more into astronomy. Can we talk about what are the fundamental limitations of discoveries in astronomy? For example, size of the telescope, image processing, the location of the Earth in terms of the overall universe.
That's an interesting way to put it. I think the biggest limitation is time. So the biggest problem is that if you allowed me to wait for a few 100 million years, then I'd understand a lot more about the universe. But we see only snapshots of what's going on. And so we don't get to, though we can get there with supercomputers, but in the real universe, we don't get to watch the processes that we're studying play out. So really the story of astronomy is about trying to compensate for that. For a long while, we've also been biased towards things that shine in the universe, right? So it sounds silly, but it's a fundamental limitation of the thing, is that we notice the things that emit, well, it used to be just optical light, but the story of 20th century astronomy is the story of learning that radio and gamma ray and X-rays and infrared have stories too. But we basically see the stuff that draws attention to itself and have to infer the physics from what's happening underneath that. But we have one great advantage, which I think it's hard to get your head around and then really profound, which is that we do get to see the past. So because the universe is large, and because light from some of the objects that we're studying has taken billions of years to reach us, we see them as they were billions of years ago. So I can't look at a particular galaxy and see its past, but if I have a big enough telescope, I can look at a population of objects, and then I can see what that population looked like 6 billion years ago, 10 billion years ago, all the way back to the Big Bang.
So you can say things at the population level.
That's right.
Not at the individual.
If you can match, right. So the tricky bit is that you have to be able to work out which objects in your snapshots of 10 billion years ago are corresponding to those galaxies or objects that we see today. And that's often the hard bit. So, for example, I mentioned the Hubble Deep Field earlier. It was a controversial measurement at the time. I write about this in the new book. Because if you took the population of galaxies that you saw around us now, today, and you placed them at the kind of redshifts, the kind of distances reached by the Hubble Deep Field, then Hubble shouldn't see any of them. Mm-hmm. And yet, when you looked at this patch of sky, we saw thousands of galaxies. And so what that tells you is that something's changed in the universe in that 10 billion years. And it turns out that in the past, the universe was much more active. Galaxies were forming many more stars, and they shone brighter. So we would say that the ratio of mass to light changes. So you get more light emitted per unit mass from a galaxy. And so, therefore, we could see these things. Often the universe has surprised us in that sort of way. Another good example is...
To clarify this, does that mean that the further out you go, like the farther you go, the more bright it is in some sense?
So there's two sets. You mean sort of the ambient light of the universe would be brighter? I think that's true. We do now see, we've gone back far enough that we see a rise. So people talk about this period of cosmic noon, which is quite a nice phrase, which was about 10 billion years ago, where there was a peak. There's also, if you're thinking about conditions for observing, there's also a background light in the universe, a thing called the cosmic microwave background, which is, we can go into detail if you like, but for now it's sort of the leftover radiation from the Big Bang, and that's been cooling over time. So it's currently in the microwave bit of the spectrum, but if you go back far enough, then more of it shines in the infrared. So you also have this background glow as well. But I was just going to say, another example of the universe surprising us is that people were reasonably reluctant to go looking for planets around other stars because it's a difficult thing to do. You generally can't see the planets themselves. You have to use indirect methods. But the teams that did that early were much more successful than they thought they were going to be, because it turns out that our solar system isn't the only way to arrange planets. So we have small planets close to the star, big planets further out. Turns out there are many systems, about 5% of stars have big Jupiter-sized planets very close to their star, and they're easier to see because they have a bigger effect on the star. So planet hunters went from thinking that they would be lucky to find one or two planets to a situation where we now know more than 5,000. And we're only now getting to the point where we would detect our own solar system. But we've already been very lucky. So it's another example of this limitation of we can only see things that shine, right? The planets aren't bright enough for us to see, so we have to detect them indirectly. You asked about telescopes as well. So there's two things that you want from a telescope. You want it to be in a good sight, and you want the mirror to be as large as possible.
What's a good sight?
Yeah, so a good sight, so in order, I think you want excellent weather. So you want as clear a sky as possible. Second, you want what we would call good seeing. So that's the stillness of the atmosphere. So if you go out on a clear summer's night, you will never have as good a view of the sky as you have in the middle of winter on a clear night, because the heat from the ground will cause the air above our heads to move, and that's what causes the stars to twinkle. So you need good seeing, and that often means being high up, so you're above as much of the atmosphere as possible. And then if you've got both of those things, the other thing you'd like would be to be on the equator, because then you can see the whole sky. You can see north and south. And so astronomers have tended to put telescopes for the last 50 years on mountains somewhere in the tropics. So northern Chile in the Atacama, Hawaii, Canary Islands, southern US as well to some extent. And then, of course, the best thing to do is it's harder on the telescope. If you can go into space, you suddenly don't have to worry about these things. And so
that's the ideal.
That's the ideal, but it's hard to launch large telescopes into space. And so the size of a mirror gives you two things. It allows you to see deeper, because if you have a bigger mirror, because it collects more light. So we talk about telescopes just as light buckets, right? You've got a bigger bucket, you get more light, you can see fainter things. But there's also the physics works out such that a larger mirror gives you a sharper image. And in space, that's what really matters. So Hubble is not a particularly big telescope, but because it's above the atmosphere, it gets these exquisitely sharp images that we can't get from down here. And then there's a creative piece, which is what you do with them. So we spend a lot of our lives writing proposals for telescopes. Most of the big telescopes are somewhere between 3 and 20 times oversubscribed. So you might spend a month or 2 months writing a proposal to use the JWST, the new NASA and ESA Space Telescope. And most of my colleagues who did that didn't get time. And so there's this competition to argue about what to use the telescopes for that also feels like a limit, even if it's not a fundamental one.
Yeah, that's something I wanted to talk about, actually.
Yeah.
I see parallels with AI and large compute clusters.
Right,
and large telescopes in the way that people compete for these resources. And for example, if you want to do serious deep learning, you need a huge GPU cluster, to train something like GPT,
Yeah.
which is not available to the average scientist.
No, and there isn't a way for... So what's interesting in that world is there isn't a way for you to bid for such a cluster, right? You'd have to find the research. I guess you'd have to get a grant with a large amount of research money. Whereas our telescopes seem to be... We often end up in modes where they're shared resources. So even...
Globally shared.
Not always. If you want to apply to the Very Large Telescope in Chile, which is stupidly named, but there you go, but is run by the European Southern Observatory, you need to be working in a country where they've paid in. But, the space telescopes tend to be globally shared. There's an idea of getting the best ideas, and the place is collaborative enough that you can usually get people. So there is this sort of open bidding process.
Yeah. So I guess deep learning is parallel to that, but much more locally. So, for example, within a university,
yes,
compete with others, or within a company.
That's right.
Some projects would be allowed to run for a longer time.
Yeah,
so
that's right, and it's almost the same thing. So the weird thing about asking for telescope time is that you need to claim that the results that you're going to get are going to be transformative, right? They're going to teach us a lot about the universe, but you also need to claim you know exactly what they're going to be. So there's a sort of art to making these arguments.
But the more transformative they are, the less you...
Exactly, yeah. And so these things, a big shift in my career was that I was for a while the world expert in sulfur chemistry in the early universe, which is a topic that I think has still only ever really interested me. But I can argue why you should care about sulfur in the early...
Was this in your high school project?
No, that was about dust grains around stars. Sulfur, this is the end of my PhD. So I started to think about so I was an astrochemist for a bit, thinking about how molecules form around stars. And the point of doing that is that it's very hard, because they're a long way away, to see a star forming. You generally see these things as blobs in shortwave radio images. And if you're a physicist, then you might be able to predict the size of the blob and maybe the temperature of it. But that's not very constraining on the models of what is quite a complicated process. If you're a chemist, we can look at emission from about 100 different molecules. And to get the relative strength of those lines right, you have to have got your model really right. So it's very constraining. So you suddenly have lots more constraints on what you're predicting about how star formation works. So being an astrochemist is a good idea if you're into star formation. And we have the idea that in different galaxies, you have different environments. You might have more high energy particles flying through the galaxy because maybe the black hole is active or something like that. And that would affect the chemistry. And then we have the idea that in the early universe, there hasn't been time to form the mix of chemicals, metals, as we'd call them, that exist in the universe today. And so sulfur, I said, was extremely important in the early universe. I was very excited about this idea. And all we needed to do was get a radio telescope to look at some of the most distant star-forming galaxies that were then known, and to look for sulfur dioxide and sulfur monoxide. And that would prove my theory right. It's one of these rare places where I had an idea and I could go and test it. And I tried 4 times and got good reviews, but no telescope time every time. And the last time I got the email that said no, I was at a conference and I was presenting with a poster. So I had a poster with my results on, and at these conferences, people come around and chat. And this guy came up to me and he kept saying, well, you should apply for time on the Very Large Array to test this, which is the telescope I've been trying to get. And I sort of politely said something, and eventually he would not let it go. And I said, look, well, they clearly don't value original research and they don't want to take a risk, and I'm really not sure I really want anything to do with such an organisation. And then I apologised, said, well, what do you do? And he said, oh, I'm the director of the VLA. So I sort of decided I should do something else with my career.
That was the name it took.
I'm sure I have no evidence that this bloke, who was perfectly friendly, would have taken a grudge, but I moved on, and this is where Galaxies took off, and I ended up doing other things. But at some point, I've actually just realised that there are now new galaxies that would be good targets for this. So I think at some point I need to go back and look for sulfur, because it was a boring enough idea that no one's thought about it in 15 years. So maybe I could go back and test it.
Interesting, yeah. So to recap, the biggest thing is time. That's limiting the discoveries.
I think so, yeah. So we would like to understand, I work partly on trying to understand the effect of merging galaxies. And this is a thing that happens in the universe. We know the Milky Way is going to collide with its neighbour Andromeda in about 5 billion years' time. But these things play out over the course of millions, if not billions of years. And we can see various galaxies in various states of merger, and we can build computer simulations that show what happens when two galaxies merge. But we're still in the dark about things like how such a merger affects star formation in the galaxy. There's people who will tell you that it's fundamental, that most stars in most galaxies form from mergers. There's evidence that, not quite merger, but the Milky Way encountered a galaxy that was about a tenth of its size about 5 billion years ago. And that came through the disk of the Milky Way. And though no stars collide, there's enough space between the stars that you don't get stellar collisions, which is slightly mind-boggling. The gas gets stirred up and you trigger star formation. So there is evidence of a peak of star formation that coincides with that in the Milky Way. And maybe you can make the argument that the sun was one of the stars formed because of this passage of this galaxy, which is quite fun. Whereas other people will say, yes, that does happen and you do form some stars, but it's like a firework display. It looks great, but fundamentally doesn't change anything. And the best way to resolve this would be to sit with a random sample of different mergers. I could probably pick 10, and I'd like to just watch them happen. And we don't get to do that, obviously. So we are in this moment of a universe, and all we can observe is what's happening now. On smaller scales, this matters too. If I want to see an Earth-like planet orbit a star, that takes a year. And so if I'm detecting that planet because of how it affects the star, I have to wait for many years to build up evidence. So there is this sort of temporal bias. There's also things like friends of mine who study transients, things that change in the sky, which is a big new field. Like people talk about time domain astronomy, watching things change in the sky. We haven't had a supernova, an exploding star, in the galaxy since the invention of the telescope. Which is beginning, and then we think there should be one of these every 100 years. So we're 400 years. So that's not a huge statistical outlier hit, but it is really annoying. It would be very nice to have a nearby supernova. It would teach us a lot, but there's nothing we can do but wait.
So for time, it seems like, other than bending the laws of physics, would you say it's just observing more and more galaxies? Because that's one way, right? If you have a huge data set, there's going to be galaxies which are very similar to each other. In different states.
Yes, that's right. So that's the game that we plan. I think the other thing that astronomy has got very good at doing is finding new ways to observe as well. So from the early 20th century, it became apparent that although astronomers were reluctant at the time to say that this was interesting, but once we got big radio telescopes, particularly after the Second World War, suddenly we could see these galaxies, we'll see the sky in a new way. What they called radio stars didn't always correspond to the galaxies that were shining brightly in the optical, so there's a new population. People have played this game with higher energy and so on. These days there's a lot of excitement about what people talk about multi-messenger astronomy, which I'm not sure the term is useful, but you mentioned gravitational waves, these ripples in space that tell us not about things that are shining, they tell us about massive things moving rapidly, so mostly merging black holes.
So that's also a new way.
That's right, and there's actually at 1 o'clock tomorrow morning, so by the time this podcast goes out, there will have been a very exciting new result on gravitational waves that I can't tell you about right now. But your listeners will perhaps know what we're talking about, but a new way of looking at gravitational waves, which will be really exciting. And then people have started to look at particles as well. So there are big experiments that look at cosmic rays, high energy particles that come through the galaxy, or neutrinos that come from distant supernovae. And so we're beginning to find that we can piece together part of the astronomical story that way as well. And if I try and introduce, I've spent an hour trying to introduce myself, which is very generous, but if I have to do it in a line, I usually say that I'm an observational astronomer, which means that I think about new ways to get information about the universe, to make the best out of what we can see. So those are often small ideas, but really nice example, which came from working with my colleagues Brooke Simmons, who's now at Lancaster, and Becky Smethurst here in Oxford, who's also Dr. Becky on YouTube. So you should look up. Yeah. We crossed the point where students were impressed to meet me, and have long ago reached the point where they're impressed by meeting Becky, which is great. So we look at bulgeless galaxies. So most spiral galaxies. So a spiral galaxy like the Milky Way is a disk. We see that. That's why we see the Milky Way in the sky. But they often have a bulge of old stars at the centre. The Milky Way
means in the third dimension.
That's right. Yeah. So the traditional way of describing this is that, don't think of pancake. Think 2 fried eggs back to back, and then the yolk in the middle is the bulge. And we found, partly with the help of Galaxy Zoo, a whole host of bulgeless galaxies, so that would sort of needle thin, edge on. And what's interesting about these is they're sort of guaranteed not to have had a merger. Mm-hmm. Because if the stars are orbiting in a disk and you throw something in, then some of them get kicked out of the disk and they end up in a spherical bulge at the centre. So these are guaranteed merger-free. And so we can use them to understand this question I was talking about of whether mergers affect galaxies. And so they're sort of a laboratory experiment, a natural experiment. We can take those and we can compare them to normal galaxies, and then we can say that perhaps that the difference is due to mergers. And so that's been a really fruitful way of going about this. But the fundamental insight was, we can look at bulgeless galaxies. They'll tell us about this question. So that's the kind of thing that I like doing.
Mm-hmm. And data size seems to be important for this, right?
Yeah, because so we had 1 million galaxies in Sloan, and our original data set of bulgeless galaxies was 113. Mm-hmm. So we started with 1 million galaxies. And so what that tells you is we need another survey, right? Because I'd actually rather have 1,000 of these things, because by the time you control for mass and star formation history and all the rest of it, you it's absurd. You start with 1 million galaxies, you can end up with 6 in your sample. And that's frustrating. So deeper surveys, as you say, some of which are coming online. But yeah, that's the kind of thing that's the kind of trick we play to try and understand what's going on.
It's very interesting because I see a lot of parallels. For example, I work in neuroimaging, and a big limitation is also the kinds of ways we can measure what's going on inside the brain,
right? And
figuring out new ways. Because we use, for example, fMRI, which is very, very limited in terms of dynamics.
Yeah,
which is quite similar because temporally we also
just because the imaging technique averages over time, right?
Yes.
Yeah.
And then we have more non-invasive methods, but those are insanely crude compared to the 100 billion neurons that fire away in our brains.
Right, and you have a similar dependence on that people do computer simulations and things, right? But it's not clear whether those represent the reality of what's going on.
Yeah, often we want real data.
Yeah.
And that's also expensive to acquire. And there's all these issues which seem quite similar.
Maybe it's a fundamental science thing. It's about acquiring the right data. I have to say I'm delighted to be in a building with MRI machines. So I funded part of my last year of undergrad. I'd kind of run out of money, which was a whole other story. But the neuroimaging people would pay 50 quid if you would have your brain scanned. And so I spent an awful lot of time hanging out, hoping for another 50 quid. So if there's a Cambridge data set from the early 2000s, I'm in there somewhere. Yeah. But I was fascinated then by the imaging and by the complexity of the data set, really.
Yeah. So really the hardware and the ways we can detect things, which is similar to astronomy, like light, radio, gravitational waves. So all these, whether we can figure out new ways, that's also
and the shift to time domain is interesting. Like, so seeing things change. So I'm involved in a survey called the Vera Rubin Observatory, which is going to do a survey called LSST, which is going to scan the whole sky every 3 nights with a telescope with an 8-meter mirror, which is about as big as ground-based telescopes currently get.
Oh yeah, I read about that.
It's got the world's largest digital camera on which now works. We've tested it; it's great.
Are they planning to put that into space?
No, this will be a ground-based survey. So that's going in. It's going on a mountain in the Atacama, mainly because we don't have a rocket yet that can launch an 8-meter mirror, but also because for a survey you want the stability of just being at the same site and doing the whole sky. But we're not ready. We've been talking about this for 15 years and we're not ready. And we're 2 years away from the start of the survey. But we think, for example, that the alert stream, which will tell you whenever something in the sky has changed.
Too much data.
20 million a night, we think, as a conservative estimate. And people are beginning to not panic, but that's a lot of information coming our way. And that'll be everything. It'll be asteroids and Kuiper objects by Pluto and flickering stars and planets and the centers of galaxies flickering as material falls into the black hole and supernovae. And, in the first month, we should have more of a particular kind of supernova, type 1a supernova, which we use to measure the expansion of the universe. We have more in the first month of the survey than in all of human history. It's going to be great. But it's exactly what you get by opening up a new way of looking at the sky.
Yeah.
So it's not a new wavelength, but it's deeper and faster than we've done before. So I guess there's a parallel there with some of the methods that are beginning to show changes in the brain and so on.
Yeah, I actually had a question about this written down because it seems like there's 2 challenges there. One is just an engineering, like storing the data, data throughput, and the other one is the selection, the filtering of events.
Yeah.
So can you speak to both of these, like how people can deal?
Sure. Yeah. I trust my friends who do instrumentation. So I'm not an expert on this stuff. I think I'm always impressed by the care and attention to detail. So a fact that stuck in my head for Rubin is that I was watching. They had a video of the camera being tested, and it has this enormous chip. I forget what it is in gigapixels. It's the world's biggest digital camera, and the shutter for it comes across, and then when it needs to move off, it rolls out the same direction, as opposed to going back and forth like a normal camera shutter. And it's because the chip is big enough that if you went back and forth, half the field would have slightly less exposure. So by going across, you get a smooth. So that's the level of detail that people are caring about, and the scale of the project is impressive too. They've had to lay their own undersea cable from Chile to the US to get the data to the data center.
Wow. Okay, so that's one way to solve it.
Yeah, exactly, and it's a huge engineering problem. It's got some interesting if you're into your database structures, it's got some interesting problems. So one thing you do is you measure the brightness of everything in the survey. And then you look for sudden changes. But it's a 10-year survey, so we're going to have billions upon billions of data points, 30 terabytes of data a night for 10 years. And one of the weird aspects is that's not big compared to Google, but Google know what's interesting.
Yeah.
The same search terms trend, and when something new happens, all right, there might be a spike, but it ramps up. We can have a star can explode, and immediately I need every data point that star has ever given, that we've ever got of that star over 10 years. But there's no way of telling half an hour before that it's about to become interesting. And so just working out how you search that database to do that is really hard. And there's been a bunch of...
Yeah, I see, because there may be future events for which you need data from
exactly.
the past.
Yeah.
That data might not be interesting.
No,
you might throw it away.
Yeah, or not just throw it away, but you may not make it easy to search for. Mm-hmm. So we're trying not to be at the stage the particle physicists are at with the Large Hadron Collider, where most data taken by the LHC isn't stored. So unless it matches a preset of filters, they throw it away. So if there was something truly unexpected happening at the LHC, we wouldn't see it in the data. Yeah. We'd see it as a loss.
Different.
Yeah. So we're trying to not quite be there yet. So then what you do is you filter this, and for some things, that's not too bad. If you care about, let's say, these type 1a supernovae, we've got a good sense of what some of the data is going to look like. So you can build a filter that's good at finding only type 1a supernovae. And because you've got more than we've ever had in human history, you probably don't care if you only find 70% of them. Mm-hmm. You've still got more than everyone else, so who cares? But the trouble is that might be a biased set of type 1a supernovae. Maybe we get the fainter ones or the brighter ones, and that will matter for the cosmology. Worse than that, if there's a new kind of supernova we've never thought to look for, that gets hard. And so the difficult bit of the problem that we're working on is, what do I show to an army of people, volunteers or professionals, to try and pick out the most interesting stuff so that we could be surprised by these data sets? And you can give astronomers a pint of beer in an hour and we'll come up with a long list of bizarre stuff that might be in the data set. But my guess is we haven't thought of the things that will be in there. But it is a filtering problem.
That's the hard thing.
Yeah.
I don't know how much you use machine learning, but is there some way you can make an automatic algorithm too?
Yeah, so we're doing bits of, we become a deep learning group really for this reason. So we do sort of probabilistic deep learning. So you can, there are good ways to quantify how surprised a trained network is by a new set of data. So you can look at the things that the machines find most surprising, or which are ill-classified by some previous set of classifications. But most of those will be boring. So we most of those will be satellite trails, which is a big problem, or artifacts, or when you see a bright star. If you've ever drawn a star on a Christmas card with spikes coming out of it, those spikes are caused by the telescope optics. Stars don't look like that, and those spikes can go across several fields. So for bright stars, they can interfere in fairly unpredictable ways. So most of this stuff will be boring. So what we're looking at is how to filter the things that the machine tells us are unusual. So we just ran a project where we had people search through a random set. No, it wasn't random, that's wrong. A selected set from a large survey that our deep learning said was interesting. And then instead of asking people to classify the data, we just said which of these is interesting. And you could think of it as trying to build a recommendation system. So in the same way that Amazon will show you, if you look at Crowd in the Cosmos, it will show you similar books, to use a random example. We're hoping, if you're interested in this, we'll hear more galaxies like that, or hear more events like that, and maybe use that as a filter.
So that's a very supervised way of going about it. But I just wonder if there's any unsupervised, state-of-the-art deep learning ways of somehow instilling this interestingness into the model.
People have done it. So that immediately makes me think of people have done it with clustering, where you do methods where you take a random data set and try and decide how many kinds of thing are in it. There's also some one-shot learning where if you've got something interesting, you find the similar things. The data set's very, very large, and I suspect that those methods, from what I can see, would be good at finding things that are in 5% of the images, but probably less good at finding things that are in 1 in a million. So maybe that would be useful too. But I think we'll have to throw everything we've got at it. And I think that's why it's fun, especially early on when we don't understand the data.
I wish companies like Google or DeepMind would set their eyes on this and come up with new techniques. I've talked to DeepMind before. I think this problem of finding the unique thing in the data set is a weirdly scientific one, though. I think if you're building an automated car, all you care about when you see the 1 in a million thing is that you're safe. So I think that you stop and you don't engage, or you don't further classify it. If you're building a search engine, the 1 in a million things no one cares about, because your performance as a search engine is going to be about things that people mainly search on. So I think there's a sort of niche here that doesn't help. We work with brilliant people in computer science who are interested in this problem. But it's going to be fun. And it's interesting, 10 years ago when we were talking about this, people told me machine learning would have this solved. And now we're 2 years out,
from the survey, and people are asking about citizen science and how to get more people involved. Yeah. There's a sort of 80-20 rule, right, which is a web development thing. But in machine learning, I think we seem to be running just hard enough to be able to do 80% of the problem all the time. And the data sets are growing, so the 80% is growing too. But we never seem to make much progress beyond being able to solve that 80% of the classification problem.
Just wanted to linger a bit more on the scheduling of telescopes and the building of telescopes. It's something I find quite interesting because, so I mentioned the parallel with AI and GPU clusters, and there it seems that deep learning researchers have been very fortunate of this research being very profitable. So it fits into this capitalist optimization framework. And a side effect of that is that the research has been exploding. So I wonder whether there's a way of acquiring more data or building better telescopes in making it more capitalistic in a sense. I don't know. How do you convince billionaires throwing money into this, basically?
Yes, we're having a rather antagonistic relationship with various billionaires as an astronomical community at the minute. But let's just talk about the machine learning bit for a second, because I want to understand the analogy. But I mean, one way of telling that story is that the size of the machine that you need to do state-of-the-art deep learning has increased dramatically over the last 2 years, but let's say the last 10 years since deep learning really got going. So, to do interesting academic work on state-of-the-art, like big deep learning, that's gone from department cluster to university cluster to supercomputer scale facilities to really, there isn't going to be a University of Oxford large language model, right? There's 3 or 4 of those that belong to very large companies who have released them or whatever. We've seen open, I don't follow the politics of it very closely, but OpenAI, which set out to do things in the open and be a resource, have turned around and said that the only way they can make it work is to be a commercial service and to keep stuff private. So doesn't that model lead you to a point where academic researchers can't work with the biggest and best models because they're locked away inside companies?
Well, I guess there's some research that can be done and some research that
can't be done. Yeah.
Because, for example, you can access the API into these models. And so one thing that's also been happening is an open source effort of reproducing these large language models. So I think there is one model now which is open source, and it's like almost as good as OpenAI.
Okay, so that's in my world, that's the equivalent of these open data sets, right? Of saying that things should be open. But that, I'm deflecting your question slightly. The argumentative bit of me wants to point out that we already have an excellent way for billionaires to contribute to science, which is that they pay tax, and that we fund as a public good the research that we want to do.
But it seems like there could be a more focused effort. I don't know if it would be possible to have a research company focused on astronomy, for example, or on building telescopes.
Yeah. Certainly there are companies that build telescopes and design them and make money that way. I'm not sure the process of running, because the data isn't commercially valuable. Now, I can make a commercial case for astronomy, right? And there's the list of spin-outs and spin-offs that we usually claim Wi-Fi as a spin-off from radio astronomy, and we can claim the camera in your mobile phone as a spin-off from what was originally military technology but was commercialized for astronomical cameras. And so there's that case to be made, but I get that's not what you're making. So here's an example. So one of the things I work on a little bit is SETI. It's looking for aliens. Mm-hmm. And for 25 years in the US, it was illegal to spend government money on searching for aliens. SETI was explicitly mandated by Congress as unfundable. Mm-hmm. And so it created this vacuum where the only thing that happened was private money Paul Allen, who was one of the early Microsoft founders, funded what's called the Allen Telescope Array, which is a set of research-grade radio telescopes that work together, but they're optimized for broadband searches for SETI. They haven't found anything yet. Much of the effort, actually a big group that are coming to Oxford, is funded by a guy called Yuri Milner, who's a Russian-Israeli-American businessman, an investor who has put millions of dollars into buying time on telescopes for SETI. So several of the biggest, best radio telescopes in the world now devote lots of their time to SETI because he's bought time. They also do what's called commensal observing, where sort of SETI is a passenger, and whatever else the telescope is doing, we search it for maintenance. But, I guess there's a model in which Yuri could have built new telescopes and then invited people to invest in this thing. I'm reasonably skeptical because I don't see what the value proposition is.
Yeah.
The philanthropy, sure, but and I'm certainly sympathetic to the argument that if you want something done in this world, then getting it aligned with the capitalist system that we live in is a good idea.
Well, that's why I was wondering. There's a way to make it aligned, but
I think it's tough. I think like I said, I think you can make. I don't want to say there aren't commercial arguments for countries and people to invest in blue sky research, and I think it's a good principle that if what you care about is the discoveries that are going to power companies and research in 20 years' time, I think it's a good idea to invest broadly rather than trying to decide now that a particular flavour of deep learning is the thing that's going to power the British economy in 20 years' time. So I think you can make that case, but I think I'm romantic enough to think about things like Robert Wilson, who was the director of Fermilab, which is the big US particle physics lab, somewhere in the 60s was asked by Congress whether the establishment of Fermilab would contribute to national defence, in other words, whether it would have a use in the Cold War. And there were many things he could have said, including that he was training a technical workforce and that spin-offs, etc., would be important. Fermilab's even been used for some particular form of medical therapies as well from the particle beam. But what he actually said was that he felt it made the country worth defending. And I just think, the fraction of the taxpayer budget that goes on astronomy is so small that I think we should try and make a case that it's just worth investing in trying to understand the cosmos. And then we get all these other benefits like training students that go off and do other things and possible spin-outs. But I think it's very difficult to say that if you want return on your money, you should build a telescope. I think that's not a great proposition.
Yeah, I mean, in the beginning, companies like DeepMind, OpenAI, they weren't making money.
True.
But I guess at least there was a path there that you could see in the future. Okay, if we build amazing AI, then that's going to lead in some ways.
And there's sort of this strangeness of we had a spin out from Zooniverse that what's the polite phrase? Ended, closed. There's a term for not having succeeded and shut down that I'm forgetting. But
flopped.
Yeah, well, yeah, there are many other words, right? Didn't work. But that was an interesting experience for me because it's not my world at all. I had excellent collaborators who helped us have a go at this. But I hadn't realised the extent to which the venture capital ecosystem is about producing things that other venture capitalists will want to invest in. So, and in the context of your comment about DeepMind, I think what that means is we have a system where they do encourage long shots because they're placing many bets and they hope one or two of them will come off spectacularly. But you have to promise that they're going to succeed spectacularly.
Yeah.
So I was quite surprised to be told that a nice little business is an insult. And I think your telescope building enterprise is a nice little business, right? We could say we're going to build all of the world's... there's one lab, basically, that builds all of the world's large telescope mirrors. But they have a customer a year or so on. So I think, even for a VC, you'd want to then claim that there were going to be that everyone was going to need one of these telescopes, and that we'd have 1 billion of them in 20 years' time or whatever.
Yeah, well, I guess...
Which is why you get investment in space, right? So rockets are a place where people are investing, partly because they're fun, but also because they're able to, with a straight face, make the claim that SpaceX or Blue Origin, which is Bezos's company, will make the claim that if they can make access to orbit cheap, then the number of rocket launches will go up by a factor of 10,000, and that they will own that space. And so you need that acceleration factor.
Yeah, but that's also can be regarded as an intermediate goal. Because, for example, why Elon Musk started SpaceX, I think the main goal is to get to Mars.
Yes.
And that's definitely not I don't think that's really a commercial.
I don't know. I think he wants to get to Mars to make money.
Yes, but that's very much in the future, so...
For sure.
It does seem, yeah.
Well, let's put it this way. I don't think he wants to get to Mars because he's interested in learning planetary geology by exploring a new planet.
Yeah.
There's some combination of money and ego there. This is what I meant when I said we're busy having arguments with billionaires, right? Because, a commercial mission to Mars is not necessarily the best thing for the science on the planet. And the language around a lot of that stuff, especially from Musk, is really problematic because it's about, colonies, and it's about a world away. I think part of the dream of Mars for him is that he sees it like some movie version of the Old West, right? Where you can build a company town where you don't have to worry about pettifogging regulation from the government that does things like, say, you have to say sorry to the people when your rocket blows up and covers them in sand. Anyway, this is deep into politics really, but I do think, access to, this next week, ESA's Euclid mission, which is a pure science mission to look at, it's going to do a survey of the nearby universe to try and answer some of these cosmological questions, like how fast is the universe expanding and what its fate will be. But it's launching on a SpaceX rocket. And it's launching on a SpaceX rocket, partly because launching on a Russian rocket isn't possible right now, but it's launching on a SpaceX rocket because using a SpaceX rocket is really reliable, it's really cheap.
Yeah.
And it's much cheaper than using the European Space Agency supported Arianes and so on. So, there are benefits from that expansion. I don't want to say that the SpaceX is a negative thing necessarily, but I don't think it's simplistically positive, and we should be careful about clothing it in the guise of science just because it's technology.
When you say the government is investing, like not investing enough money in astronomy, astrophysics.
Always, obviously. Yeah, give me another...
So you're not happy with that?
Well, I think one of the interesting things about astronomy in particular, so I think all scientists believe that we should have more funding. And particularly in this country, with what's happened in the last few years, you can see that the investment in research has dropped, and that's bad. Partly because we know good things happen to the economy when you invest in blue sky science. But I think one of the interesting things about astronomy is that, this is worldwide, but there's a good American example of this, is that if you do an opinion poll that's a reasonable sample, people will tell you that they think the government shouldn't waste so much money on NASA. Mm-hmm. Now, most of NASA's budget is not Astro, it's the Crude program and various other things, but that's fine. But they'll say, that's a waste of money. And then you ask them, how much of the government budget do you think NASA spends? And the answer is usually between about 10 and 15%. And the real answer is, I think it's about half of 1%.
Yeah.
And so the perception of the amount of money that goes into this stuff is enormous compared to the value. So I'm prepared to cut a deal with the American public, and we'll take a NASA budget that's only 1%, which would make an enormous difference. We're arguing now about building the next generation of observatories in space, which will be an American, European, Japanese, worldwide consortium, I'm sure. But with the current funding level and the current way, then maybe one of these will fly in 2050.
Ooh, that's quite fun.
And from a purely selfish point of view, that's too long. There's stuff we want to do with these telescopes before then. So I do think that the amount of money spent on this stuff is really rather small, and I think it has benefit. But we have to argue for those benefits in a way that isn't, we will produce better Wi-Fi for you next year. Yeah, because then we're going to lose out. So yes, of course we'd like more money, and of course I can justify that. But it's about the type of money as well. Undirected, like, science moves at the pace of people. Funding things is one thing. I can fund a space mission or whatever, but it's really, if you want to accelerate science now, then we could do some more postdocs on long-term fellowships. People who have 3 years just to do research or 5 years just to do research. And the number of jobs like that exist has been really squeezed in the last 20 years. So yeah, give us more bright people and they can do great things.
All right, let's circle back to science for a bit. How did you become interested in studying galaxy formation and evolution specifically?
It's a good question. I think there was this opportunity. So my science, I've always been, we've already said, I'm an observer, but I'm kind of ambivalent about what I observe. I got interested in galaxies via getting interested in star formation. So I did my PhD partly on how stars form, and then realised that we suddenly had all this data from Sloan, from galaxies. So for the first time, we really could ask population level questions of galaxies, that it wasn't about looking at 40 or 50 galaxies, but we had data for 1 million. And so that was really exciting to me. And it's a place where it's not really, I like messy problems. So although I'm a theoretical physicist by training, I'm not really a write down equations on the board kind of scientist. And so galaxy formation and evolution should be a straightforward problem. It's just gravity and then some chemistry and what occasionally dismissively gets called gastrophysics that happens within the galaxy. And so we understand those processes, so it should be easy. It's very rich, complicated, complex behavior due to the interplay of all the feedback that happens. You form a star, that star explodes, it then might stop nearby stars forming, but it could also, the shock wave could trigger further star formation. These galaxies have a large black hole at the center. We don't really understand why or how that grows, but as material falls onto that black hole, it's very hot. It's a very efficient way of turning material into light, actually, it turns out, throwing it towards a black hole. And so that can have a strong influence on the rest of the gravity. And then, as I've said, they interact and they respond to their environment. So it's a nicely messy problem that responds to observations, and new ways of observing. So it's really that's the richness of the observing and the richness of the phenomenology that's fun. And it's close enough to being a kid looking through a telescope trying to work out what a galaxy is that it speaks to me there.
Mm-hmm. Is the messiness not coming from the two broad level assumptions, so not going enough into the details of the physics of the interactions?
I think that's right, but it's not that there's unknown physics. So the astronomy, I tell a lot of my students that astronomy has a characteristic set of problems which are all solved at the one sentence level. So if you ask me, it's easy to see this with star formation, right? If you ask me how a star forms, I can say to you on a different podcast where we didn't have a couple of hours, I'd say you have a cloud of gas and dust, it cools and collapses under its own gravity until the density gets high enough that nuclear reactions can start, and that's a star. All of that sentence is true. You ask any other question and it starts to unravel. If you ask, well, what determines the size of the star? If you ask what triggers that process, if you ask how much of the material ends up on the star and how much in the disk that will form the planets, if you ask whether a particular star will form planets, if you ask where this happens in the galaxy, we don't know the answers to any of those things. And so you can have a sentence or you can have a textbook, or at least a decent review article. And galaxy formation is another one of these problems where I can make you a nice computer simulation that will start with the conditions that we know existed in the early universe and will produce something that looks like the distribution of galaxies that we have today. But as soon as I ask, well, how big are the black holes in those galaxies? Or where is the star formation in those galaxies? Or what's the inference of interactions, suddenly our simulations break down a bit. And you're right, it's just about, if I could track every molecule and every atom, then I think we know the physics that we would apply. Yeah. But the computer simulations have to make these abstract assumptions. Plus, there's also the case that we have ingredients in the mix of those computer simulations that we don't understand. We know that most of the matter, we think we know that most of the matter in the universe is this dark matter, which doesn't interact with normal matter except through gravity. And we don't understand what that is.
Yeah, so that's one example where physics is a bit...
Yeah, exactly. Yeah,
an unknown.
That's right. Yeah. So we would like to know what type of particle the dark matter is. It's nice to know what the universe is made of. So one of the things, so you can get surprising access to it. So, for example, the way to think about a galaxy is that it's a lump of dark matter with ordinary matter at the center, but it's the halo of dark matter that shapes the big properties of the galaxy. And the temperature of the dark matter, like how much it interacts with itself, and how fast the particles move, sets the size of those halos. And so we know that dark matter can't be made of fast-moving particles, because otherwise you wouldn't be able to create galaxy-sized halos. So that's a nice result that came out of studying galaxies that told us something about the dark matter, ruled out a whole load of ideas, like, for example, that the dark matter might be neutrinos, which are a small neutral particle we know exists, and so it'd be quite nice to build the universe out of neutrinos, but you get a universe that's not lumpy enough compared to our observations.
How could you infer that galaxies contain this dark matter here?
So,
because you cannot detect it.
No, exactly. So this is back to this thing about being biased to things that shine, right? So one way to do this is to look at the movement of the stars. So, or actually, more accurately, to look at the movement of the gas in the disk. So, one strong set of evidence for dark matter came from the work of Vera Rubin and others in the 70s and 80s, where they looked at the rotation, what's called a rotation curve. So you look at material in the galaxy, and as you move outwards from the center, you look at how fast it's rotating around. And what you find is that the outer regions in particular are rotating much faster than they should be if all there was the visible matter. So one way of putting it is it's behaving much more like a bike spoke than a solar system. So in the solar system, the outermost things move more slowly. Bike spoke, obviously, you move together. And that latter behavior is what happens when you have continuous mass being added as you go outwards. And so either gravity is wrong, and there are people who think that our understanding of gravity is wrong, or there's more matter there that we can see. And you can play this game on different scales as well. So there's a now famous result from a guy called Fritz Zwicky, who was this, I suspect, was a complete pain to be around, but has got a series of anecdotes that make him seem lovable. So he would carry around a petition that he should win the Nobel Prize and force people he met to sign it. And he believed that firing a shotgun through the dome of an observatory improved the seeing, made the images sharper. So he'd do that and things like this. But he was a very, very smart observer. And he saw on the scale of clusters of galaxies, he measured how fast the galaxies were moving. And you find that if all that's there are the visible galaxies, you can work out their pull on each other. And you discover that the galaxy cluster should evaporate in timescales of 1 to 10 million years. And yet we see them everywhere. So they can't be transient objects. And so Zwicky said, okay, there must be dark matter here. And it turns out the amount of dark matter you need to keep the galaxy cluster together is about the same as the amount that you need to keep the galaxies together. So now you've got a harder problem, because I could still solve both of these results by changing gravity. But now I've got to change gravity in the same way to explain behavior on two different scales, which is much harder. And then,
so it's less likely.
Yeah. Or it's just harder to find a theory that does that neatly. And then if I'm going to change gravity, I need to not break the solar system. And then there is cosmological scale evidence for this dark matter as well when we look at the universe on larger scales. So we infer the presence of dark matter, and it's about as secure, I think, as anything that we can't capture or look at. It would be really surprising if we're wrong about all of this. But we still haven't got any direct evidence for dark matter, despite people looking in all sorts of ways. So
what are some other characteristics of dark matter that
we
understand?
It's hard to answer that question definitively. I think that it would satisfy all the observations if the dark matter was made of massive neutral particles. So a nice model would have a particle that's about the mass of a copper atom, but neutral, so it doesn't interact with light. And we just need to fill the universe with those, and then their gravity would come together. That would work fine.
But we would detect those, right?
Or
the special probability is that it's not interacting.
Yeah. So then you have to worry about so then the question is, how does it interact with normal matter? So gravity produces the effects that we see that I've described, but one way to detect them would be to look for a head-on collision with a normal atom where other forces, the forces that normally control the behavior of particles in an atomic nucleus, would become important. And so the assumption is that the dark matter would also feel these forces. So we can work out the density of such particles. So if you hold your hand out, then something like 10 billion dark matter particles a second would be passing through your hand, which is a strange thought. And almost all of them would go straight through the Earth without getting close enough to another atom to cause this recoil. But astronomers build big targets of tanks of xenon is favoured, so a noble gas that's not reactive. And you put the tank in a environment underground. Particularly, there's a big experiment called Xenon at the Gran Sasso laboratory, which is this amazing place in Italy. You drive up into the mountains from Rome, into a tunnel through one of the mountains, and then you suddenly turn off, and there's a large door, and you put in a code like a Bond villain, and it opens up, and you're in an underground laboratory. It's an amazing place, and you're there because you want to hide from high energy particles that bombard us on the surface. And there's this big tank of xenon, and the experiment is to leave it there for 5 years, and they look for flashes of light that should be triggered by the recoil of one of these particles if a dark matter particle hits it. And they're hoping, I think they have 1,000 tons of xenon, and they hope for 5 collisions a year. Now, the frustrating thing...
There's a lot of other things colliding as well.
Well, less so in a quiet environment like that.
So
And so you can find... There is a point you can't keep making these experiments bigger. There's a point where you become sensitive to the radioactivity of the rocks around you. So there's what's called the floor. So this will probably be the last generation of these experiments. Now, the problem is that you're measuring two things. You've got how many pings you should get depends on how massive the dark matter particles are and how likely they are, how close they have to get to score a direct hit, which are both properties of the particle. And the problem is that our experiments can rule out some combinations of those, but there are loads of combinations of those factors that would still satisfy what we see in the sky, but which wouldn't produce detections. So we can't rule out dark matter by doing this. We can only rule out some kinds of dark matter.
Yeah.
People had hoped perhaps that the Large Hadron Collider would produce some exotic particle. If the Large Hadron Collider, in its high energy collisions, produced neutral particles, then that would be really exciting. But we haven't seen anything like that since. So we're still slightly in the dark. And I would say probably 90% of working cosmologists believe in dark matter, but there's 10% who think we should change gravity, and there are various ideas about how to do that.
Well, belief is always a weird word in science.
Well, no, but I think that's true, except that in this, I guess I'm passing it in this case as choose to use that model in their work.
Yeah.
So, which it can be belief based, I think. You know, it's you might write it down as an assumption or something. So one way you could attack this is some people would say these theories of alternative gravity predict different things about how fast galaxies appear in the early universe, because that's a place where gravity is very important. It's shaping what's initially quite a smooth distribution into the first galaxies. And JWST, which is this new space telescope that launched a year and a half ago now, is looking for the first time at large numbers of galaxies right in the first billion years of the universe's history.
Which are really far away.
Yeah, exactly. So the way to put it is their light has been travelling towards us for more than 13 billion years. And the preliminary results are that there are more of these than we expected, or that they're brighter than we expected. And if that holds up, then that will be I'm sure they'll get much credit, but that was predicted by the modified gravity people before the mission. And they would say that that's a result that could be easily explained by changing gravity rather than sticking to dark matter.
And there's no way to predict that with dark matter?
It's not the obvious prediction we can predict the number, because we for simple dark matter, then you get a different prediction. So that's kind of interesting. Now, there's a lot of work to do to see whether this result holds up. So you'll have to have me back on in a year and a half and we can talk about whether that's held up or not. But it's interesting to see. There's a big argument about... We are seeing these things, but they look like tiny red blobs. And a lot depends on how you interpret the spectra of those blobs to come up with a mass of a galaxy and so on. And there's much argument going on with that at the minute. But... the trouble with the dark matter thing is you can also have non-simple dark matter. So you can start to invent theories where the dark matter interacts with itself, where you may have some dark physics, right? There may be forces that the dark matter feels that we don't. Some sort of dark charge or something. And then theorists have fun playing with these things. But I think you want to be forced to such complexity, I think.
Well, I mean, does it even matter what the interactions are within itself? Because if all we can measure is the interactions it has with non-dark matter.
Well, if the interactions that it has with itself causes it to clump together faster, then you get more massive galaxies early on. So you get like a bonus gravity boost or something. No, there's no reason to expect dark matter to have that, but people would also say, well, we don't understand the physics of it, so I can invent whatever I like. But it's an interesting time that we're trying to attack this, and we haven't even mentioned dark energy, which is it's a terrible name. I don't really know what it means for energy to be dark, but it's this. We've discovered that the expansion of the universe is accelerating.
Yeah.
And
dark energy.
Yeah. The joke is, I'm not sure this was coined by an American physicist. The British word for it for a while was quintessence, which is the Greek fifth element. So they have, fire, earth, water. What's the fourth one?
Air.
Air, thank you. And see, we've got medieval astronomy, medieval science down in Oxford. So quintessence was the fabled fifth one, which I thought was quite nice because there's four forces and then this must be a fifth force that's acting against gravity on large scales. But the joke is that the Americans realised that if you called it dark energy, the Department of Energy, which funds fundamental particle physics, could be persuaded to fund research into dark energy. And if that's true, then it's working very well.
But it's really a force, right?
That's one way to think about it, right? So I think it's an easy way to see why it's a problem in our theory is that if you look at two galaxies, we know that the strong and weak nuclear forces act only on the scale of atoms, so we can ignore those. We know that galaxies aren't charged, so there's no electrostatic or electromagnetic force going on. And so you've only got gravity, and gravity is an attractive force. So the idea that the universe is speeding up tells you that there's something else going on.
So their dark matter couldn't play a role.
Correct,
because...
yeah, exactly. So in fact, dark matter is opposed to this, because dark matter is a label for having extra gravity.
Yeah, exactly.
And so dark energy is a real mystery. So far... people have looked at most of the effort from, I mentioned the Euclid mission, and Vera Rubin is partly funded to do this too. We're trying to measure a parameter called W, which measures whether the influence of dark energy is getting stronger over time. And the idea here is that if it is, and we can measure that, or weaker over time, that would be a strong clue to what it might be, because then any theories of it would have to account for the change.
So again, there's the question of time. And
that's right. And so we can look backwards in this case. So we can slice the universe and say, okay, how fast was it expanding here and here and here and here, and then measure the. So far, there's no evidence that dark energy is anything other than a sort of that contributes the same per unit space from the beginning. And the current generation of experiments will establish that to within a decent error. And then it's not clear what we do with dark energy, I think. I think we're waiting for a theorist to come along with a compelling explanation of what it is. Like from some understanding of what space is or something. It's as fundamental as Einstein coming and explaining gravity by telling us that space-time existed.
So far the understanding is it's been quite constant throughout the life of the universe.
So constant with scale. So it appears to scale with size. So if you ask the sort of energy density of dark energy per unit volume, that's constant across the course of the universe. But of course the universe is getting bigger, so dark energy becomes more important over time.
Interesting.
So the universe started off expanding for some reason, slowed down under the influence of gravity, and then about 8 billion years ago started to speed up.
So there was this threshold
where that's right. Yeah,
and energy became more important.
That's right, just because the universe got bigger. And we're beginning to be able to see enough epochs of the universe to see that story in detail.
So is that like a linear scaling with the size?
Yes. Yeah, exactly. So that so the clue that you would derive from that is to say that it's likely to be a property of space. You get more space, you get more dark energy. And there are various quantum physical ideas about why empty space should have this sort of repulsive force, but explaining why it has a force that's relatively weak. So you often see, the claim's not quite right, but you could do a naive quantum calculation that says, okay, if empty space has such a repulsive force, how strong a repulsion is it? And the answer you get is 10 to the 120 times larger, so that's 1 followed by 120 zeros, larger than the force we observe.
So the math is not quite.
Yeah, so it's been called the biggest error in physics, and I think you can hack away at that. So people get it down to like only an error of 10 to the 80, but we don't know what to do next. So
just to understand better, does that come from the fact that when the universe is expanding, there's somehow more space?
That's right.
As well?
Yeah, so that's why it becomes more influential over time. Yeah, exactly. So if that continues, the expansion of the universe will speed up and speed up and speed up and speed up. And this has various depressing consequences for astronomers, like
not being able.
The fraction of the universe that we can see drops.
Yeah.
Stuff disappears over the horizon. So this is my best argument for funding science now, is the proportion of the universe that we can see is dropping.
Well, yeah, but now is relative.
Yeah, that's true. Yeah, all right. You should fund astronomy in the next 10 billion years or so. Yeah, something like that.
But so how is space understood then? Is it at the level of quantum physics? Or?
So I suspect the answer to dark energy is some unification of quantum physics and relativity. So for an astronomer, we tend to think about space through a relativistic lens, in which relativity describes space as sort of an entity that can expand and which has properties that allow it to transmit gravity and so on. As I think lots of people know, relativity disagrees with quantum mechanics, and then our theory of the vacuum comes from quantum mechanics. So we've learned that the vacuum is not a static place, so the particles appear and disappear in what is apparently empty space all the time. And there are experiments one can do in a lab that can measure the effect of one of these virtual particles. There's a thing called the Casimir effect, which shows that there's a pressure that's caused by the appearance and disappearance of these particles. But those two theories aren't compatible with each other at a really deep level. One way of thinking about it is that they disagree about what time is. So in quantum mechanics, time is an observable. It's a thing you can measure, and it acts like an observable. It has uncertainty, which is a fundamental in quantum mechanics. In relativity, time is a coordinate. It's like space. So we will often talk about space-time as a four-dimensional thing. And so that just means that the two theories don't talk to each other. And that comes up in astrophysics in a place like trying to understand black holes, trying to understand the Big Bang, places where gravity is important and the small scale is important, and we don't have a unified theory. And my guess is that dark energy, when we get a unified theory, dark energy will make sense, because it will tell us something about the quantum properties of the vacuum that will say that there should be a repulsive force of about this strength. But it's possible the observations are wrong. I don't think that's right, but it's possible. And we're nowhere near having such a theory that we can test.
Yeah, I mean, it is an interesting prospect of whether resolving this contradiction would answer like some of these deep.
Yeah, I think that a lot of the excitement about dark energy is that it's a thing about, almost, if you're a theoretical physicist, almost the worst case is living in a universe where we can explain all the observations, because then there's nothing for your theories to hang on, right? Theorists want their ideas to be proved, mostly. And so dark energy is and dark matter to some extent are big things about the universe that we don't understand.
Yeah.
And so being able to attack them with observations and with theory is really exciting.
So maybe this is a weird question, but I wonder what makes more sense to ask. Is there more stuff, objects in the universe, or more space? Or how would you answer that?
So the universe is really empty. Yeah. I think this is one of the things that it's very hard to internalize. When I talk to the public, I think sometimes it's very easy to give the impression that I know what it's like to say there are 100 billion galaxies, each containing 100 billion stars, and I have no conception of what that actually means. I can just say the numbers because I've said them a lot. And space is incredibly empty, to the extent that if you were at the top of the Earth's atmosphere, and let's ignore the expansion of space for a minute, and you travelled to the edge of the observable universe with your hand held out, then on average, what you would pick up on your hand during that journey would be 2 grains of dust. And that's it. I said earlier, when 2 galaxies collide, there's so much space between the stars that you don't get any stellar collisions. So the fact there's anything is really remarkable.
Well, mathematically it's really empty, but at the same time it's incredibly full. Like there's so many things, right?
Well, it's very big,
you said,
right?
billion.
Yeah. No, it's very big, and we get to see the things that exist. So yes, it's vast, I would say, rather than full.
So, Are you more stunned by how many things there are in the universe, or how many things there aren't, or how much space there is? Like, which is more? Weird?
No, I see what you mean. I think the more alienating thought is that the universe is mostly empty. Like, I think that's hardest to get my head around. Like, I still, in thinking about it now, I'm thinking of stuff in the universe, right? I'm trying to get a sense of space being empty by thinking about the space between galaxies and galaxy clusters. There's an amazing, incidentally, novel by Pippa Goldschmidt, who used to be an astronomer and is now a novelist, who wrote about an astronomer that ends up contemplating the cosmic voids and going mad because of it. Although the book's about other stuff too. So I think that's the weirdest thought. I think the thought I have most often, and that I find inspiring, is the variety of object that we find in that vastness. That, going back to planets around other stars, the great adventure of the last 20 years is discovering that almost any kind of planet that we can imagine exists out there somewhere. Everything from science fiction we've ticked off, I think. Planets with 2 stars in the sky, done. Planets that keep one face to their star, done. Planets that are hot enough that their entire surface is lava, done. Planet that's actually a giant diamond, we found one of those too. So the diversity of things that one finds in this vast universe is I think, awe-inspiring. And
I guess you would argue that this comes from the vastness of the universe.
Yeah, we've rolled the dice so many times, I think. But often we think about that as a familiar thing, right? Because the other argument you can make is, we do make, and it's an important scientific question, which is that planets like the Earth must be very common, like for whatever your value of like the Earth is. we're almost certain that there are billions of Earths out there, with a few caveats. So there is this weird familiarity to it as well. In this diverse universe, we can find places that would look very much like this, with the caveat that we don't know whether the life is common. But we could find you a planet that was that had the right temperature and conditions for our kind of life in almost any corner of the Milky Way and almost any other galaxy. So we have this awe-inspiring vastness, but a very familiar places within it. I talk about this, actually a lot of this is in the introduction to the new book, where I'm trying to talk about, not very successfully, but I'm trying to talk about this, the two-headedness of this, of being in awe of the vastness but finding a place within it. And one of the examples I use is a really down-to-earth one almost, which is looking at images from the Mars rovers online. So talking about open science, if you follow Mars Curiosity or Perseverance, the two NASA rovers, as soon as data hits the ground here on Earth, it's put online. And so if you're online at the right time and you refresh the page at the right time, you can be the first person to see an image from Mars. And most of those are really boring, right? They're images of calibration targets, or, with apologies to geologists, they're images of a rock that may or may not get probed by the rover. But occasionally, for navigation purposes, it takes a landscape shot. Yeah. And they're stunning. Yeah. Partly, I think, because the rover cameras are about 6 foot above the ground. So it feels like a very human view. And so you can imagine standing there. And I've had the experience of pulling up an image, and one of the things I do for fun is I'm a hill walker, and so you look at that landscape and my brain immediately goes, okay, so you could go up there and then you'd get to the top of that hill and then you could transverse across it. It's a landscape I can imagine being in. Although it's very alien, no vegetation, red rocks, dusty sky, I have this very familiar experience to it. And then there's one of these images that shows an evening star in the sky, and that's something, I step out my house here in Oxford in the last couple of weeks, and Venus has been beautiful in the sky. Your listeners should listen to the much shorter Dog Stars podcast that I do with my dog, talking about this stuff. But in this particular shot, the star in the evening sky on Mars is a double star. And then you suddenly realise that's the Earth and the Moon. Mm. And you take what was this very familiar experience, and suddenly it's a completely alien experience. Yeah. And I think there's something of that in looking at the distant universe as well. You have that sense of seeing us magnified and reflected, but also this sort of very alien perspective on our own thing. And none of this is that's not a very scientific response to your question, but some of this is why I do astronomy. It's fun to have those things.
Yeah, I mean, I'm very interested in human intuition and how we can sort of think, visualize these things, because that's also important, this kind of understanding, as well as the mathematical, physical. So I was wondering, as someone who looked so much at galaxies, how would you describe the true size of the universe, or how can you intuit? I just wish there was a way to truly experience.
Yes, I think that's right. And I think I do too. And I think we give the impression as science communicators and astronomers, like you listen, I like Brian Cox, I think his stuff is excellent, but you listen to Brian and he gives the impression that he knows what it's like to live in a universe with 100 billion galaxies. I've also had a drink with Brian, and he has no profound understanding of that any more than the rest of us do. So I don't know how to experience that. Maybe there's this Hitchhiker's Guide, had Douglas Adams' wonderful novels, had the infinite, what's it called? The infinite perspective vortex, right? Where people go mad because it actually made you experience the vastness of the universe, and you would go mad as a result.
So maybe we don't want to do
that. Yeah. Zaphod Beeblebrox doesn't, because he's got such a huge ego that he just thinks that he's the most important person in all of it. And so maybe there's a solution there somewhere. I don't have a good answer. I have written things like, there are more stars in the universe than there are sand grains on the surface of the Earth, which is nice. Also, we're not sure that's true, and we're not sure it's true because we don't know how many sand grains there are on Earth, although it's about the right order of magnitude. But I'm not sure that helps. I think I could do it in steps, right? So we live on a planet around a star. If you go out at night, then with the naked eye, from a dark site, you can see maybe 1,000 stars at any one time. So that gets us to 10 to the 3. Then you see the Milky Way from a dark site, which is mostly the light from stars we can't resolve, but that's probably another, let's say, 100,000 stars contribute to that. So that's that far. But then you've got to jump to the galaxy being 100 billion. And at that point, I think I'm lost. I don't know what that... And then I have to just do... And then there's 100 billion galaxies. So yeah, I don't know. I don't know how to do that. I think...
I just imagine with like proper computer graphics or like VR, there could be a way to...
Well, we can fly through the Sloan, right? So we've got this three-dimensional map of the universe, and we can fly through it. And that does give you this sense that space is empty.
Yeah.
Because you do suddenly see that there's gap. The other thing that's stunning is that there's structure on these large scales, that the galaxies aren't randomly scattered. There are places with lots of galaxies and there are places with very few. Mm-hmm. And that structure tells us about how gravity has shaped the universe as well.
So they're clustering.
That's right, yeah. There's almost a honeycomb structure to the universe. And that structure seems important. So maybe one way to get your head around the larger scales that we can see is to think of it as this structure, like looking down on the night side of Earth and seeing humanity set out by lights shining in the darkness. Mm-hmm. Maybe that's the way to think about what we're seeing, that the galaxies are lighting up this vast cosmos. I will, I can. So we can do bits of that, and that's fun. But I don't think it, because you're looking at a screen or because you're in a headset or whatever, I just don't think you're really getting a sense of the scale of it. After all, Sloan's what, 1 million galaxies, so that's 10 to the 9, 10 to the 6, 10 to the 11, so that's 1 in 10,000 of the galaxies in the observable universe. So that's roughly the same proportion as a single opinion poll, if you actually invest. So that gives you some sense of what we're doing in our cosmic senses.
So what happens when you go outside of the observable universe? What's out there? Well,
we're assuming that our observable universe is a tiny part of a much larger whole.
What is that assumption?
So the observable universe is set by its time again. So the observable universe is the part of the universe where light has had time to get to us. And so if you ignore the expansion of the universe, then that would be increasing in size. And it's possible that you get to a point where we see an end. But there's nothing we see that suggests that that's going to happen. So there are observations that suggest that the whole universe must be much larger than the tiny bit of it that we can see. Many people believe the universe went through a period of very rapid expansion very early on called inflation, which would then mean that our bit of the observable universe is much, much less than a billionth of the whole.
Wow. So rapid inflation in this case means faster than light.
Yes, space is allowed to expand faster than light. So the rule is that nothing can travel through space faster than light, but space itself isn't bound by that rule. Yeah. And that explains some features of what we see if you have this period of rapid inflation, but we don't have any direct evidence yet that it happened. So we have to assume that our bit of the universe is representative of the rest. Otherwise, we can make no progress in trying to understand it. So we can check that, for example, by I can look at one side of the sky and check that the observations I make of the distant universe in that direction are statistically the same as that which we see in the other direction. Because if there was some large-scale change, then you might see a gradient or something. Maybe there'd be fewer galaxies or more galaxies or different galaxies. And we don't see any sign of that. So our assumption seems okay, but it is a fundamental assumption that we're looking at a representative bit. And there was a brief vogue where people tried to explain away dark energy by saying that we were in an unusual part of the universe, but I don't think those theories work.
It's interesting because in my mind, as someone who doesn't do astrophysics, I thought the observable is the bigger part. So there's like a band around it, which is escaped from us. But no. We're just a...
Yes, so it's another of these cosmic perspective bits, is that we're only a tiny part of the whole. And that's even before you get to the idea that there might be other universes, of course, which people enjoy speculating about. We are really have this tiny bubble as part of a vast cosmic ocean that we get to explore. And we get to see it now.
It could very well be the case that it's actually not representative.
Correct. I think that's right. Yeah, exactly. And so maybe if there is some large scale, then you can get into anthropic arguments, right? So you can start to say, well, let's say you have a grand universe in which all the physical constants change, so the speed of light changes, the strength of the atomic forces change. Then it's not weird that we find ourselves in a bubble where the constants happen to make for a complex universe that can support life. And so people have used that sort of argument to explain some aspects of what we see. There's some fine tuning that's required for hydrogen to be able to build helium, which is what happens in the star, and then for helium to be able to build in other stars heavier elements. If the properties of the atomic nucleus and the atomic forces are slightly different, that becomes much harder. And yet we live in a universe where those things happened. And so you either need to explain that from fundamental physics, which we're working on, or you just say, well, it varies across the whole universe, and of course we're in a bit where we got lucky.
Interesting.
Because otherwise, why are we here? It's the same as a lottery winner asking, why do I live in an enormous house? You know, and is it surprising that I live here and won the lottery? Well, no, they're causally connected. So yeah, there's that sort of argument too.
In the case where it's changing across the wider universe, it's even harder to reason about what's going on.
Yeah, exactly. And so what the best we can do is people have looked to see, for example, if the fundamental atomic constants were changing, then spectra from distant galaxies should maybe look different from nearby ones, and we don't see any evidence of that.
Yeah.
So we think that the speed of light is constant within the errors that we can measure them with across our observable universe. Yeah. But if there's some grander thing going on, it will be very difficult to access.
So I guess asking the question of what happens at the edge doesn't even make sense.
Yeah, that's right. This is one of these questions that I have you've hit several of them so far. There's a small list of questions that come up a lot, whether you talk to anyone from 8-year-olds to 80-year-olds, that I don't have a good answer to. And that is one of them, because it's impossible not to visualize the universe as a thing with an edge. But it may not make sense, like in the sense that if you travel, if you ignore the expansion, if you could just travel through the universe, it can have a shape and it may not have an edge. So in the same way that if you walk south and just keep doing that, you don't hit the edge of the Earth. You just end up you're at the South Pole and then you can walk north again. So we don't know what the shape of the universe is. It can be finite and bounded without having a brick wall or an edge. But I understand that's not an intuitive answer, and that I probably haven't helped.
No, I mean, there's no answer to this question.
Yeah.
Zooming back a bit on galaxies, I guess we went a bit ahead, but could you explain what the current understanding is of galaxy formation and evolution?
Sure. We've touched on bits of this. So we know from observations of what's called the cosmic microwave background that the early universe was slightly lumpy. So there were places in the universe that had slightly more matter than their surroundings. And we know that gravity can act to exaggerate those changes. So if you have a place that has slightly more matter, going back to our story about capitalism, the rich get richer and the poor get poorer, right? So particles tend to accrete to parts of the universe that already have more matter. So those differences become exaggerated. Within some of those with the densest parts, the first stars will form. And we think that the first stars were massive compared to the sun. And that means they're short-lived. So they probably live for only 1 million years or so. And then they explode as supernovae. We're hoping maybe we could catch the light from some of those supernovae in the next few years. And that spreads material that's made in that explosion from nuclear reactions that happen in the explosion that produces the first carbon, oxygen, nitrogen in what until then had been a universe made almost entirely of hydrogen and helium. And then normal star formation can kick off. At the same time, these galaxies are merging with each other. Gravity continues to act to produce galaxies with a range of sizes and a range of star formation histories. until we get to what we see today. The other actor that matters, we think, in this time is that at the centre of the galaxies early on, we think maybe just because the density was high enough, large black holes formed. So objects that are large enough that not even light can escape. And they will have continued to accrete matter over the course of the history of the galaxy, perhaps constantly and perhaps in bursts. Mm-hmm. When that happens, as I said earlier, as material falls onto the black hole, it heats up and it shines brightly. You can also get jets of material that are powered by magnetic fields that grow up around the black hole. And so these black holes can have a strong influence on the rest of the galaxy, but we're not sure of the details. And like I said, that's my good few sentence answer. And if you ask no more questions, then we completely understand galaxy formation evolution. That almost every sentence I've given you, you could write a thesis on almost every word, because we don't understand the details of any of that stuff, or haven't yet managed to test those things.
What would you say was the biggest failure in your academic journey?
Well, almost all of my thesis is wrong, but it was interesting to do at the time, I think. I've been really lucky, not because all my ideas are right, but because I've got to work with good people, and in good places where I've been supported. I think it's a really good question. I'm somebody who works on an awful lot of different things, and at almost any time in my career, I should have stopped and concentrated on one or two things, rather than taking on more tasks and more ideas and more collaborators. On the other hand, that's the fun bit. But yeah, I think probably I should go back and divide stuff. That's from the academic stuff. From the science communication thing, which has always been a strand of my academic practice, I wish I'd realised earlier that standing on stage, telling people what you know is fun, but isn't the most interesting way to have a conversation. Mm-hmm. And that I wish I'd earlier found a way of talking differently about what we were doing to audiences. I spent an awful lot of time giving talks that were, here's everything, I had a talk that I gave many, many times called something like everything you want to know about cosmology that we're afraid to ask, one of those things. And it's such a one-way. The interesting thing is the conversation that the audience wanted to have about cosmology, not the 6 things I wanted to tell them. And that's been a long and slow journey of realization for me. So I wish I got there earlier. Also, it would be great if money flowed freely so that I didn't have to write grant proposals and that everything did depend on what money we could get in to do various things.
Yeah, but that's not...
No, I know, but yeah.
Do you think there are limits to what science can explain? For example, are there aspects of the universe that will always remain mysterious, or is time the only limit?
I don't know. It's possible. There's no requirement on the universe to be explicable by us. So it's possible that dark energy, for example, we will never explain. There's nothing fundamental about the human brain that says we were capable of creating a unified theory of quantum gravity. And there's nothing about the universe that says it has to arrange itself in such a way such that we could measure the critical evidence. There are ideas in cosmology in particular, like the idea that, I really like the idea that in the long run a universe can produce new universes, that some process which we don't understand can produce new big bangs out of our ever-expanding universe. And there are various, I can even tell you particular flavours of that theory that I find appealing. My guess is that that's not a testable proposition. But I think the joy is trying. And so I don't think there are questions that we should stop asking. There's no, just as there's no guarantee that, my football team are going to ever have a decent season. There's no guarantee that the universe has to let us win. But the point is playing the game.
All right. Well, that's a very good point to stop this on. So thank you for having this amazing discussion.
My pleasure. I've really enjoyed it.
I hope to have you again.
Yeah, do.